Okay, let's wrap up our talk of periodic trends by thinking about the last three things we need to talk about. Um, this involves dealing with different kinds of energies involved with stuff and metallic character. Things I need us to remember that are going to come up as us again. This effective nuclear charge is, this looks like ELF again. This effective nuclear charge business is going to be important, as well as this idea of carrying cost for electrons. Remember, we talked about that with relation to those weird electron configurations as we do it. Um, yeah, those are two real big themes you gotta pick out here. All right, so there's three trends we're going to talk about. First, we're going to talk about ionization energy. Um, ionization energy. Now, part of the issue with the trends that gets to be confusing is that the same couple of things controls all of the trends. But we've talked about atomic radius, and atomic radius and ionization energy kind of go together trend-wise, okay? We said with atomic radius, as you go down a group, the radius gets bigger, and as you go across a period, the radius gets smaller, okay? The opposite is true for ionization energy. As you go down the group, the ionization energy decreases, and as you go across the period, the ionization energy increases, okay? And this is all due to effective nuclear charge, right? Okay, so as you're going down a group, I always think down a group is a little bit easier to explain or to grasp. As you're going down a group, the atoms get bigger, right? We physically have more stuff, right? There's more electrons. So if you think about it, lithium has 3 electrons. Cesium has 55 electrons. Okay, which one is going to care more if you take one of them away, right? Lithium is going to care a lot more uh, because it it only has 3, so it's going to notice one is gone a lot more. Cesium has 55. It doesn't really care. It's like, here, take it. I don't want it anymore. Okay, so it's easier to remove from the cesium than it is from the lithium because the effective nuclear charge is smaller. Okay, we see the same trend in the noble gases, right? Helium has a very high ionization energy, and as we go down the group, it gets smaller because the effective nuclear charge is increasing, okay? So if you remember, effective nuclear charge increasing means that the electrons are held more tightly, so that makes our atoms smaller, but being held more tightly also means that it's going to take more energy to get rid of that electron. So what we're thinking about here in terms of ionization energy is losing that first electron. So this is all done in the gas phase, which I think is weird, but whatever, it's how they do it. Sodium turning into a sodium ion and releasing an electron. It doesn't matter what element we're talking about. All we're doing is we're talking about giving it energy and kicking out that first electron that's there. Okay. Uh, yeah. Going across, oh yeah, let me go back. Going across the group, the trend is that it should increase as you go across. And it does that, right? Effective nuclear charge. But if you look, there's a couple of spots in here where it's kind of not holding true. So like here you can see them, and here you can see it. As you get farther down, like in here, now we're talking about transition metals, and transition metals are weird, so we're not going to stress about it in this course. All right, so why do we get those jumps in the weirdness here, right? The trend should, I mean, and in general, the trend is that it increases as you go across the group, but there's some discrepancies. It's not a smooth trend. This is where we have to worry about pairing cost. Okay. If you have an electron that's loose on his own, it's very easy to get him to leave because you're going to get back that energy out. If the electrons are paired up, it's going to be more difficult to remove. Okay. That's what we're talking about here. That's this gap. If we look, sorry, I don't know what's wrong with me today. If we look at this little gap, that's between nitrogen and oxygen. So this is nitrogen and this is oxygen. It's easier to remove this electron in oxygen because it is paired up when the other ones are not. Remember we talked about a half-filled subshell. So here's a half-filled subshell. It's going to be hard to remove this guy because you're getting rid of the half-filled subshell. Here, what you're doing is you're getting back your pairing energy cost, right? It's actually lower energy to unpair those electrons. So it's easier to remove the oxygen one than it is the nitrogen one, okay? I'm not going to stress too terribly much about it, but that's where those little blips come from. If you have more than one electron, the atom is going to have more than one ionization energy for it. We call these successive. So the first one we just talked about, then there's second, third, fourth, etc., depending on how many ions you're taking out. Where am I at? Okay, so what we're looking at is taking out electrons one at a time. Remember we said most main group metals will lose all of their valence electrons, and that happens kind of all at once, but we can kind of strategically measure them. Let's look at sodium again. The sodium for the first ionization energy, we just talked about sodium in the gas phase going into a sodium ion in the gas phase, and losing an electron, okay? The second ionization energy is taking the 1+ ion and kicking out a second one to make a 2+ ion and releasing another electron, right? The third, it's the same idea, right? The trend continues, 2+, kicking somebody out to become a 3+. Now, it's weird because sodium shouldn't form a 2+, or I should write 3+, shouldn't form a 2+ or a 3+ because it only has one valence electron, okay? But let's look at the data. Here's our first ionization energy, not too bad. The second ionization energy is 10 times as much than that. Each one of these gets higher. That is a trend. Each successive ionization energy increases because it's a higher effective nuclear charge every time you take away an electron. Okay, so it gets harder and harder to keep removing electrons. Okay, right. So this big jump happens because, okay, we've removed that first electron from the sodium. The rest of these are part of the noble gas core, and it's really hard to break the noble gas core. So what this saying is that there's one electron that's easy to remove, and the rest are really hard. That's one valence electron. If we look at nitrogen, we see the same thing, right? Here's one, and there's two, it goes up, three goes up, four goes up, five goes up. Then there's a ridiculous jump to go to six. We went from 9,000 to 53,000. Okay, the ridiculous jump is when we're breaking the noble gas core. So that's what we want to watch out for. You can identify what element we're talking about by thinking about where that giant jump is in the ionization energy, right? Since the big jump happens at ionization energy number 6 for nitrogen, that would mean that we have 5 valence electrons there for him as we do it. Okay. Now, the next one we're going to get on is electron affinity. And electron affinity, you can kind of think of this as the reverse of ionization energy, right? Instead of trying to take an electron away from the atom, you're going to give the electron another electron. You're going to give the atom an electron. Sorry. Okay. So for example, this would be like if we take a chlorine atom in the gas phase and give it an electron, we can make a chloride ion that's in the gas phase. This is what we're talking about in terms of electron affinity, okay? Now you'll notice here all these guys have positive values. Did they have negative values on this? No, they didn't. Okay, not gonna stress. Okay, so the way I think about this is I like to think about electrons and affinity. Oh crap, I'm getting a call. Give me 1 second. All right, I knew that was going to happen. My truck's in the shop and they were calling to say it's ready to go. Anyway, so there's an economic parallel here about atoms and electrons and energy, okay? Electrons can be bought and sold using energy, right? If you're going to take an electron away from an atom, you have to give it energy to get that electron back. Okay. If you're going to give an atom an electron, the atom is going to give you energy back. Okay. So that's just one way to think about it. So here we're looking at how much energy do you get back when you give an atom an electron. Okay, that's the electron affinity. The trend here, and the trends get a little bit shakier. As you go down the group, there's no trend down the group. No trend going down. That, I don't know what that says. No trend going down the group. As you go across the period, there's kind of a trend, but it's less of a trend than it is knowing what the electron configuration of something is. Okay, and we can see there's no trend going down the group because fluorine, chlorine, bromine, iodine all have very high electron affinities. Lithium, sodium, potassium, rubidium, cesium all are relatively low, and they're all kind of the same, right? And there's some down here that are like, they're never, ever going to do it, okay? And let's dive into this a little bit. This is all about, electron affinity is all about where is that incoming electron going to go, okay? Remember, our goal is to have 8 valence electrons. Okay, halogens have 7 valence electrons, so it's super easy, and they really want to get another electron. So they will pay whatever cost it is to get that electron, because then they'll have 8 and they'll be happy and stable. Okay, let's look at some of these other ones. So again, if we're thinking about this, so you can kind of think of it as the electron affinity should increase as you go across, but again, just like the ionization energy, there's some little blips here. Our first blip, I'm trying to remember because they didn't label everything. So lithium, okay, lithium, and then beryllium goes down, and then we're going across nitrogen, boron, carbon, nitrogen goes down, oxygen, and then fluorine. So if we think about it, this would be, say, lithium in group 1. It's very easy to put an electron there, okay? If you're going to go into beryllium and try to give it another electron, it has to start a new subshell. Starting a new subshell is bad. Starting a new shell is bad. It's not going to do it. It costs too much energy. Okay. Here, if we look at this, this is carbon. Okay. Carbon, it's very easy to add one more to carbon because now it has that half-filled subshell. Remember, half-filled subshell is good. Okay. If we go over one to nitrogen, nitrogen is not going to want to do it because nitrogen has a half-filled subshell. If you give it one more, you're pairing them up. That's a pairing cost, and the pairing cost is too much. Okay, so we kind of want to think about that. It's all about where is that electron going to go, and how much does that atom want to pay to have an electron there. It's not going to start a new shell. It's not going to start a new subshell. These ones that dip below that are actually negative are noble gases, right? There's neon. Neon's not going to take one. There's argon. Argon's not going to take one because that's starting a new shell. Starting a new subshell, starting a shell is bad, okay? Pairing is bad, okay? Getting a half filled is good. Getting a filled is awesome, okay? That's what they want. All right. Lastly, let's talk about metallic character. You kind of already know this. We just got to point it out that it's an actual trend across the periodic table. Remember, metals are over here. Non-metals are over here. And the metalloids are in the middle there. Okay, so there's a trend. Metallic character, this is how much like a metal something is. Okay, increases down a group and decreases across the period. Okay, things that are metals, when I think about it, are going to have a low ionization energy because they need to lose their electrons to form compounds, and they don't want to gain, so they're going to have a high electron affinity. Okay, so there we go, and they kind of parallels those trends. Okay, and you can see them. I love this figure. This is from an older book that I used before. I love this figure because it shows you all the things: sodium, magnesium, aluminum. Then we have our metalloid, silicon, and then non-metals, phosphorus, sulfur, and chlorine, and then the same thing going down. Nitrogen is a non-metal. There's phosphorus. Arsenic is a metalloid, and then antimony and bismuth. Okay, so know our trends, know what they mean. Okay, this is a nice summary. Remember, we talked about atomic radius before. Atomic radius, we have those trends. This is all about effective nuclear charge, right? Effective nuclear charge increases as you go across. Effective nuclear charge increases as you go across. Effective nuclear charge increases as you go across. Ionization increases as you go across. Okay, so know the trends, know we can compare stuff, and know why the trends work the way they do. Okay, if you need me, I'm here. Feel free to ask questions, and I'll catch you later.